panel inspector's concerns stem from the fundamental principle that every component within an electrical panel must be capable of withstanding the maximum potential fault current. This viewpoint is rooted in safety, as a component lacking the appropriate fault current rating could fail catastrophically, potentially leading to electrical fires or other dangerous situations. The argument is that the overcurrent protection device, or OPT, such as a fuse or circuit breaker, should act as the primary limiter of fault current. The idea is that if the OPT is rated to handle the available fault current, then any component downstream should be adequately protected, even if its individual fault current rating is lower. Analyzing this situation requires careful consideration of several factors. Firstly, electrical codes typically mandate that all components within a panel must be rated to withstand the maximum available fault current. This requirement aims to ensure the panel safety across all conceivable fault scenarios. Secondly, from a safety perspective, it is generally considered best practice to utilize components rated for the maximum available fault current. This approach minimizes the risk of component failure and associated hazards. Thirdly, practicality plays a role, as sourcing components rated for the full available fault current may be challenging or even impossible in certain instances. This can create difficulties in complying with code requirements and maintaining a safe installation. When facing such challenges, several potential solutions may be considered. One possible solution involves the use of isolation transformers. Installing an isolation transformer between the power source and the panel can effectively reduce the available fault current to a level that allows the use of components with lower fault current ratings. However, this solution can be relatively expensive. Another solution involves upgrading the components within the panel. If feasible, replacing existing components with those rated for the available fault current may prove to be the most cost-effective solution in the long run. A third solution entails limiting the available fault current through the use of current-limiting devices, such as reactors or specialized fuses. While potentially complex and costly, this approach may be necessary in certain situations. In summary, the optimal solution depends on the specific circumstances and available budget. Consulting with a qualified electrician is crucial to determine the most appropriate course of action. Now let us go into the details of the mentioned terms. Let's first talk about fault current. Fault current is the electric current that flows in an unintended path, usually due to an insulation failure or short circuit. It is often much higher than the normal operating current and can cause significant damage to equipment and pose a serious safety hazard. The magnitude of the fault current depends on several factors, including the voltage of the system, the impedance of the fault path, and the available fault current from the source. Impedance in an alternating current circuit is the measure of the circuit's opposition to the flow of current. It's similar to resistance in a direct current circuit, but it also takes into account the effects of capacitance and inductance. Capacitance is the ability of a component or circuit to store electrical energy in an electric field. It's measured in farads. A capacitor stores energy by accumulating electric charge on two separated conductive plates. Inductance is the property of an electrical conductor by which a change in current through it induces a voltage in both the conductor itself and in any nearby conductors. It's measured in henries. An inductor stores energy in a magnetic field created by the current flowing through it. Overcurrent protection devices, OCTs, such as fuses and circuit breakers, are designed to protect electrical circuits from overcurrents, including fault currents. They interrupt the flow of current when it exceeds a predetermined level, preventing damage to equipment and reducing the risk of electrical fires. Fuses are single-use devices that melt and break the circuit when the current exceeds their rating. Circuit breakers are reusable devices that trip and interrupt the circuit when the current exceeds their rating. They can be reset after the fault has been cleared. Isolation transformers are transformers used to isolate electrical circuits from each other. They provide electrical isolation between the primary and secondary windings, preventing the transfer of direct current or unwanted noise. Isolation transformers can also be used to reduce the available fault current, as the transformer's impedance limits the amount of current that can flow through it. Reactors, also known as inductors or chokes, are passive electrical components that store energy in a magnetic field when current flows through them. They are used to limit the rate of change of current in a circuit, which can help to reduce the magnitude of fault currents. Current-limiting fuses are a type of fuse specifically designed to limit the magnitude of fault currents. They have a high interrupting rating and can quickly clear faults, protecting downstream equipment from damage. The National Electrical Code, or NEC, is a widely adopted standard for the safe installation of electrical wiring and equipment in the United States. It provides detailed requirements for overcurrent protection, equipment ratings, and other aspects of electrical safety. Underwriters Laboratories, or UL, is an independent organization that tests and certifies products for safety. UL listing indicates that a product has been tested and meets certain safety standards. When selecting components for electrical panels, it is important to consider their fault current ratings. The fault current rating of a component indicates the maximum fault current that the component can safely withstand without failing. All components in an electrical panel should have a fault current rating equal to or greater than the available fault current at that point in the circuit. Available fault current is the maximum fault current that can flow at a given point in an electrical system. It is determined by the voltage of the system, the impedance of the source, and the impedance of the conductors. The available fault current can be calculated using fault current calculation software or by using simplified methods based on the transformer's impedance and the system voltage. When determining the available fault current, it is important to consider the worst-case scenario, which typically occurs at the service entrance or main distribution panel. The available fault current decreases as you move further away from the source due to the impedance of the conductors. There are several methods for reducing the available fault current. Firstly, using current-limiting devices, such as reactors or current-limiting fuses, can reduce the magnitude of fault current. Secondly, increasing the impedance of the circuit by using longer or smaller conductors can also reduce the available fault current. Thirdly, using isolation transformers can limit the fault current that is available on the secondary side of the transformer. Proper coordination of overcurrent protection devices is essential for ensuring electrical safety and reliability. Coordination involves selecting opts with the appropriate ratings and characteristics to ensure that the opt closest to the fault will trip first, minimizing the impact of the fault on the rest of the system. Time current curves are used to analyze the coordination of opts. These curves plot the time it takes for an opt to trip at different current levels. By comparing the time current curves of different opts, it is possible to determine whether they are properly coordinated. Selective coordination is a type of coordination in which the opt closest to the fault always trips first, without causing any upstream opts to trip. This is achieved by selecting opts with appropriate time current characteristics and interrupting ratings. Performing a short circuit study is essential for determining the available fault current at various points in an electrical system and for selecting appropriately rated components and opts. A short circuit study involves calculating the fault current that would flow in the event of a short circuit at different locations in the system. The results of the short circuit study are used to determine the required interrupting ratings of opts and the fault current ratings of components. The interrupting rating of an opt is the maximum fault current that the opt can safely interrupt without being damaged. Opts must have an interrupting rating equal to or greater than the available fault current at their location. The withstand rating of a component is the maximum fault current that the component can safely withstand for a specified period of time without being damaged. Components must have a withstand rating equal to or greater than the available fault current at their location. When selecting components for electrical panels, it is important to consider the ambient temperature. The ambient temperature can affect the performance and ratings of electrical components. Some components may need to be derated if they are installed in high-temperature environments. Proper grounding and bonding are essential for electrical safety. Grounding provides a low-impedance path for fault current to flow back to the source, which helps to trip opts quickly and prevent electrical shock hazards. Bonding connects all metal parts of an electrical system together to create an equipotential plane, which minimizes the risk of electrical shock. Regular inspection and maintenance of electrical panels are essential for ensuring their safety and reliability. Inspection should be performed by qualified personnel and should include a visual examination of all components, as well as testing of OCTs and other safety devices. Maintenance should include cleaning, tightening connections, and replacing any damaged or worn components. When working on electrical panels, it is important to follow all safety precautions. Firstly, always to energize the circuit before working on it. Secondly, use appropriate personal protective equipment such as gloves and safety glasses. Thirdly, follow lockout/tagout procedures to prevent accidental energization of the circuit. Arc flash is a dangerous electrical hazard that can occur when a short circuit creates a high temperature arc. Arc flash can cause severe burns, blindness, and even death. Arc flash hazard analysis is a study that determines the potential arc flash hazards in an electrical system. The results of the arc flash hazard analysis are used to determine the appropriate personal protective equipment that workers must wear when working on energized equipment. The arc flash boundary is the distance from energized equipment within which a person could be exposed to a dangerous arc flash. Workers must wear appropriate personal protective equipment when working within the arc flash boundary. Lockout/tagout procedures are used to prevent accidental energization of electrical equipment during maintenance or repair. These procedures involve disconnecting the equipment from its power source and placing a lock and tag on the disconnect switch to prevent it from being turned on. The tag identifies the person who is working on the equipment and warns others not to energize it. Electrical safety standards, such as the National Electrical Code, provide detailed requirements for the safe installation and maintenance of electrical systems. These standards are designed to protect people and property from electrical hazards. It is important to be familiar with and follow all applicable electrical safety standards when working on electrical panels. Proper training is essential for anyone who works on electrical panels. Training should cover electrical safety, troubleshooting, and maintenance procedures. Qualified personnel should have the necessary knowledge and skills to perform their work safely and effectively. Electrical panels should be installed in a clean, dry, and well-ventilated location. They should be protected from physical damage and exposure to moisture. The location should also provide adequate access for maintenance and inspection. Electrical panels should be properly labeled to identify the circuits they serve. The labeling should be clear, accurate, and up-to-date. This helps to prevent accidental disconnection of the wrong circuit. Electrical panels should be kept free of obstructions and clutter. This helps to ensure that the equipment can be accessed quickly and easily in an emergency. It also reduces the risk of fire hazards. The use of surge protective devices can help to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, power outages, and other events. Surge protective devices divert the surge current to ground, preventing it from damaging sensitive equipment. Harmonic distortion is a type of electrical pollution that can be caused by nonlinear loads such as electronic devices and variable frequency drives. Harmonic distortion can cause overheating of equipment, misoperation of protective devices, and other problems. Harmonic filters can be used to reduce harmonic distortion. Power quality monitoring is the process of measuring and analyzing the characteristics of electrical power. Power quality monitoring can help to identify and diagnose power quality problems such as voltage sags, voltage swells, and harmonic distortion. Energy efficiency is the practice of using less energy to perform the same task. Energy efficient electrical equipment can help to reduce energy consumption and save money. Power factor correction is the process of improving the power factor of an electrical system. Power factor is a measure of how effectively electrical power is being used. A low power factor can result in increased energy consumption and higher electricity bills. Power factor correction can be achieved by installing capacitors in the electrical system. Demand management is the process of controlling and reducing peak electrical demand. Demand management can help to reduce the strain on the electrical grid and lower electricity costs. Demand management strategies include load shedding, peak shaving, and demand response programs. Renewable energy sources, such as solar and wind power, can be used to generate electricity. Renewable energy sources are sustainable and environmentally friendly. They can help to reduce our reliance on fossil fuels. Battery energy storage systems can be used to store electrical energy. Battery energy storage systems can be used to improve power quality, provide backup power, and enable the integration of renewable energy sources. Microgrids are localized electrical grids that can operate independently or in conjunction with the main electrical grid. Microgrids can provide reliable power to critical facilities and enable the integration of renewable energy sources. Smart grids are electrical grids that use advanced technologies to improve efficiency, reliability, and security. Smart grids enable two-way communication between the utility and consumers, allowing for better control and management of the electrical grid. The information above is for educational purposes only. Consult with a qualified professional before making any electrical decisions.